Welcome. In this video, we're going to start the study of the integral. So we're going to see the concept, the types, methods, and applications. Now, usually when one find the area of polygons, for example, a square, a triangle, we have square, triangle, rectangle, circle, and many others, we have standard formula. But now imagine if you want to find the area of something that is non-standard, like for example, the area under this graph here. Of this function f of x here. You want to find the area here. Now, to find the area here, we cannot use the same formula as we know any other standard formula, because this is a curve and this curve is defined by a function, so it's not a constant as we usually do when we're dealing with the regular polygons. In order for us to solve this, we have to use some techniques. If you want to find the area under this graph over here, what we can do is, first of all, we can try to divide the area under this into different shapes. These shapes are shapes which we can easily find the area, and then we sum them up. Now, you can, for example, make a rectangle here and then another one here. We can just continue dividing this into many rectangles as we want. But now, the overall idea of what we're trying to do here is that because we don't know how to find the area of something like this, of a curve like, and a curve like this, we know how to find the area of a rectangle. So we're trying to include rectangles in to fill that area, and if you can find the area of each rectangle here, we can then sum up all these areas of all these rectangles, and we're going to have an approximation of the overall area under the graph within the given interval. Now, as we do so, you can notice that we have here some area that's not going to be accounted. This area here also we're going to have this area that is outside of our domain. This area is also outside of our domain. This area here is not being accounted. So there are many problems, and these problems are going to result in a very low accuracy. So one of the ways to tackle this kind of problem is if we try to make smaller and smaller rectangles, thinner and thinner rectangles. So what you're going to have is a rectangle here, another rectangle here, and another one here, and we do it so on. Now, why the difference when we do with thinner rectangles is that we are reducing the distance that bounds the rectangle, we are reducing it, but we are also increasing the number of rectangles that we're going to need. But on the other hand, the advantage is that we are going to have here less unwanted areas, which are these areas here that are going to be accounted, but they don't give us anything. So the result of it is that we're going to get a more accurate value, a value that's more closer to the actual value of the area under this. Now, if you keep on increasing the number of rectangles by decreasing their width, what you're going to have is that this difference here between this and this one is going to become something we can call as dx. Now, why will we call as dx? We call as dx because here, this I'm going to call, for example, delta x. Now, delta x is large difference between 2 points, x1 and x2, let us say. But dx, because I'm taking a very small elemental distance, I'm considering it to be dx. This is what the principle of integration is. We are dividing whatever the area is by a very large number of rectangles, and those rectangles, they have a very small area, but if we sum up all those areas, we're going to have what is the actual value of that integral, and so forth. Now, this is very good for us because we can solve problems involving curves like this, bounded by the x-axis. Sometimes we may have, for example, another function, let us say a function here, g of x. You have a function g of x. Now, you want to find, for example, the area that is between these two graphs here, area under these two graphs here. Now, this you cannot solve by any other conventional methods. Only by integration we can do so, and we can find the area between these two curves. When we do integrations, like for example in this first case, we can do the integration until whenever the function ends. So a function can continue like forever, and then we're making integration without boundaries. Now, if we make an integration without boundaries, which means we just continue dividing these till wherever we want, then this is called indefinite integral. Now, but if you have two boundaries that define where do we exactly want area, like for example here, I want area from A to B. I want area from A to B. I have boundaries now, this and this, so this is going to become a definite integral because it's between two definite place. So this is the symbol we use, and then we put here wherever the function we're dealing with, and here dx, integration of f of x dx. This is also called antiderivative because it gives us the reverse of the derivative. Now that is important because it tries to predict what was our original function. Say for example, you have a function, we can see f of x is equal to 2x3 plus 2. Now if you want to find the derivative of this function, which we have studied how to solve, we can apply the power rule here. What we're going to have is 6x squared plus 0. Now the integral, which is also called antiderivative, it will try to predict what was this initial function from this derivative. So we're going to have here integral of this function here, we say 6x squared dx because it was with respect to x. Now see, we are not bounding this between two different places. It's an indefinite integral. If it was a definite integral, we would have these boundaries here represented here. This would be the top and this would be the bottom. So from a to b, that's how it would be if it was a definite integral. But in our case, it's not a definite integral. So if it's not a definite integral, we don't write these boundaries here. This is x. Now this is going to be equal to the rule for such kind of function. We have a power rule for integration, says that you have to add plus 1 on the power and then divide by that new power you have. So what you're going to have here is that you're going to have 6 into x raised to 3. We are adding 1 to this power 2, divide this by this same power here, 3, and then this all is plus c, a constant c. So if you solve this, you're going to have 6 divided by 3, you're going to have 2 raised to 3 plus c. Now this c is a constant of integration, which means this function can predict but cannot predict with accuracy what was the value of our constant in the original function. This is obvious because the derivative of a constant is always equal to 0. So if it was derivative of 3 or 4 or 5 or whatever the number would be, it will always be 0. So it cannot predict exactly which value that was, and hence we can find that this function here is a prediction of the initial function, and therefore we consider them to be antiderivative. Now the knowledge we have of integral is very important because we can find the areas of almost anything that you can define by a function. It is also useful because we can find volumes of very complex shapes. There are various methods: substitution, also called UDU, by parts, UDV, trigonometric substitution, partial fraction, many methods that we're going to cover in this course. Thank you.